Hi, welcome to lecture 6 of MATH336. This is section 1.5 on linear first order equations. So today we're going to be learning about how to solve a linear first order equation, which is an equation that you can put into the following form here. And the reason why it's called linear is because it's linear in y and derivatives of y. So this is just a first order equation. So there's just the first derivative. So it just has to be linear in terms of this and this, right? So it means that it has to be like, something plus times the first derivative plus something times y. And these things that are in front of here are just functions of x. So there should be no y's in there. So no function of y here, no function of y or a function of the derivative. So it's just of this form. And we can always assume that we can put it into this form where the coefficient of the derivative here is 1. That's why we don't have any actual term here. So it's going to be a linear differential equation if it can be put into this form. So that's what a linear first order equation is. And in this section, we're going to learn how to solve a differential equation of this form. And then we're also going to see a really nice application of first order linear differential equations. So first of all, let's get started here with how we're going to solve this equation. And I came across a really nice idea when I was watching some videos from the YouTuber Michael Penn, who has some really great YouTube videos. And I'll put a link to the actual video that I watched that where he describes this idea I'll put that up on Blackboard. So the idea is that you take this differential equation here, and we're just going to multiply it by a function rho of x. And we'll figure out what rho of x should be in a second, but let's multiply by it first, and then we'll see what we would like rho of x to be. So what condition rho of x should be. So when we multiply that equation by rho of x, then we're going to get this term over here. And if we look carefully at this term on the left, it almost looks like a product rule, right? So if you were doing product rule, you would be doing like, let's see. So what is the product rule? I don't know where to fit this in. Maybe I'll just write it here briefly. So we know product rule, it looks like, well, maybe I'll put it like this, right? So this form down here, it's almost like that, right? We have something times the derivative of y, so that's like f times the derivative of g, and then we have, something times y, and that y is kind of like g here. So what that tells us is that we would like, maybe we would like to find a rho of x, a function rho of x, so that this plays the role of f prime. And what is f? F is this. So that means we would like this to be equal to the derivative of rho. Oh, and by the way, I keep calling this rho because this is the Greek letter rho. It looks like a P, but not quite, right? So a P would be like this with this, you see that little hat up there. So that's a P. A rho you draw like this. So I start at the bottom and go around, whereas P go down, everyone knows how to do a P. This is not a P, it's a rho. It's actually sort of, it's like the Greek letter equivalent of the letter R. Right, so that's rho. Okay, so rho of x, we want rho of x so that rho of x prime is equal to rho of x times P of x. So that's what we want. Now, this is kind of amazing what's happening here. So we write down this condition that we want. We want rho prime to equal rho times P. And that's actually a separable ODE. And we just learned last time, in the last lecture, how to solve separable ODEs. So let's do that. Let's solve this separable ODE and see what we get. So let's rewrite this as follows. So instead of writing, rho prime of x, we'll write d rho dx, and that's going to be equal to rho times p of x. So this is separable, right? We take this rho and we move it down there, and we take this dx and we move it up there, and then we integrate both sides, right? So that's what we get right here. There we go. So we just move that around, and now on the left-hand side, it's just an integral of an integral with respect to rho, and on the right, it's a integral with respect to x. Okay, well the integral on the left, we know what the antiderivative of that is. That's the natural logarithm of the absolute value of rho. And on the right, we don't know what p of x is, so we're just going to leave that as the integral of p of x dx. But we will add this constant here. And actually, this constant, we can kind of forget about it, as we'll see. But for now, I'm just going to put that constant in there. So we take the exponential of both sides. So that leaves us with absolute value of rho on the left. And on the right, I distributed the exponential as we've seen before. So we get the exponential of that integral times the exponential of C1. And then we get rid of the absolute values, and that gives us a plus minus here. So we'll just call this whole thing here, we'll call that capital C, and that gives us our general solution for the separable differential equation. However, if we look back at what is rho of x doing for us, well, we just need anything that satisfies that differential equation. So let's just choose the simplest possible solution that we can get for this, and that would be when c is 1. Of course, just let c be 1, and we could choose c equals 0. Oh, no, we can't. No, this c always has to be non-zero. I guess I could write that in here somewhere, because I did that before. So note that c has to be non-zero. Although I guess when you have c, when you have c equals 0, actually that would be a solution. But that would be a bad choice, because if we multiply by 0, we just get 0 equals 0, and our differential equation disappears. And I guess that's one way to deal with a differential equation that you don't like. But we want to solve the differential equation, so we're going to choose c equals 1, and we're going to get this as the formula for rho. So there it is. And it's actually a very simple formula. So we just take that p of x function, we integrate it, and then we take the exponential, and that gives us our function rho. Okay, so now that we have this rho function, we're going to go ahead and plug that back into our linear first order equation. And what do we get? So recall that our linear first order equation was of this form after we multiplied by rho of x. And when we use this fact here, this term will now become rho prime of x. And there it is. There's our product rule right there. That's a product rule. That's perfect. That's exactly what we wanted. So what's so good about a product rule here? Well, that means that we can now write this product rule as the derivative of rho of x times y. Why is that a great thing? Because now we can integrate. So we integrate both sides, and we're going to get rho of x times y is equal to the integral of the right hand side plus c. Now this constant we have to keep. So that We actually need that constant there, so don't forget that one. And then finally, we divide by rho of x on both sides, and that's our final solution. There it is, right there. So the only thing that we need now in order to remember this method is we're going to need a couple things. We're going to need to compute rho, so that we'll have to do one integration to compute rho of x. And then we're going to have to do another integration to compute the integral of rho of x times q of x. And then that's it, now we're done. So that's how we can solve first order linear differential equations. All right, so let's do an example and see how we can use this in practice. Okay, so this is a linear first order differential equation. And we can see that it's a linear first order because we have something times y prime plus something times y. So this is linear in y and the derivatives of y. But it's not in the form that we want. Remember, the form that we want to have a 1 times the first derivative. So the first thing we'll need to do is divide by x, and that will put it into the standard form that we have above. So let's do that first. So dividing both sides by x, we get y prime plus 5 over x times y is equal to 7 times x. Okay, so therefore, what is our p of x? So this is p of x right here, and this is q of x. So let's just write that over here. So p of x is equal to 5 divided by x, and q of x is 7x. Okay, so remember, this is not your p of x, right? You have to make sure that you have a 1 in front of the derivative, and then you can determine what p of x is. So p of x is not 5, and q of x is not 7x squared. Okay, so let's go ahead and now compute rho. So we know the formula for rho of x. It's the exponential of the integral of p of x dx. And we're going to get the exponential of the integral of 5 over x dx. So that gives us the exponential of 5 times the natural log of the absolute value of x. Okay. At this point, it's important to note that, let me just put this here. At this point, it's important to note that when we look at the initial condition, the initial value of x, or the x's that we're interested in here, are around the initial x of 2, right? So they're going to be positive x's. And what that means is that since we're looking at positive x's, then this absolute value of x, we can replace it with x, and just know that we're doing that because that's the side of the of 0 that we're interested in. So let's write that down here. So just a quick note, x0, which is the initial x, it's 2, right? So that's positive. So we will take x to be positive. So we're just going to restrict ourselves to positive x, and that will help us because we can now get rid of that absolute value. So now that we've made that observation, we get rho of x equals the exponential of 5 log x. And what can we do with that 5 log x. So we know that with logarithms, we can take the 5 and put it up here as an exponent. So we get the following: exponential of log x to the 5th. And finally, the exponential and log cancel each other. And so we get rho of x is equal to x to the 5th, right there. So there's our rho of x. So now that we have rho of x, let's go and multiply both sides of the differential equation by rho of x, and just make sure that it is definitely a product rule, and then we'll proceed from there. So let's go ahead and multiply that differential equation by x to the 5th on both sides. So we have x to the 5th times y prime. Well, make sure you're multiplying the one that's in standard form. So it's this one, this 5 over x times y, and then we're going to multiply on the right-hand side as well by x to the 5th times 7x. Okay, so let's see what we get. X to the 5th, y prime, plus 5x to the 4th, right, because we're dividing by x there, and we get this. Okay, and indeed we do see exactly what we wanted, right? This is definitely a product rule, because we have something times the derivative of y plus the derivative of that something. And look, so if you take the derivative of x to the 5th, that is 5x to the 4th. So that's exactly what we wanted to see. And then of course times y. So this is definitely a product rule. So let's write that out. So this is going to be the derivative of the product of x to the 5th times y. Right, so the derivative, the product will be the first thing times the derivative of the second thing, that's this. And then it'll be the derivative of the first thing times the second thing. And that gives us that. So that's perfect. It's always good to like do these double checks as you're going along to make sure that you haven't made a mistake. If that part doesn't work out, by the way, that's why I like checking it. If that part didn't work out, that tells us that we made a mistake when calculating rho. So very good idea to always check that. Okay, so let's see. Oh, right, so now we integrate both sides. So let's integrate both sides, and we get x to the 5th times y is equal to the integral of 7x to the 6th dx plus c. I guess I could call that C1, but actually that is the final C that I want, so I'm just going to leave it like that. And then we divide, oh wait, let's compute this integral first. So the integral is going to be x to the 7, right? That's, yeah, if I take the derivative of x to the 7, we get 7x to the 6th. Okay, so that's right. So plus C, and now we can divide both sides by x to the 5th, and we will get y is equal to, so x to the 7th divided by x to the 5th. Well, let me write this out maybe in full. So make sure that you're dividing the whole, right-hand side by x to the 5th, right? So you definitely want to do that. And then when you do the division, make sure that you distribute across the sum, right? So you need to divide the x to the 7 and also divide the c. So in the end, we get x, oops, we're on Penn. So we get x to the 7 divided by x to the 5th, that's x squared. And then we get plus c over x to the 5th. And that is our final answer. And often with these final answers, we like to, write y of x there like that. Okay, let's put a nice box around this. So there's our general solution of our differential equation. And now we just need to, figure out what that c is using the initial value. So let's go ahead and figure that out. And I'm just going to add a page to my notebook. And I think I should definitely pause while I do that. One second. Okay, so there we have it. We've got our general solution, and now let's use our initial condition. So I forget exactly what that is. It's y of 2 equals 5. Okay, y of 2 is equal to 5. So let's write that down. Y of 2 is equal to 5. And when we plug 2 into this formula, we get 2 squared plus c divided by 2 to the 5th is equal to 5. All right. So let me see. Okay, this is 4 plus c over, okay, 2 to the 5th. That's going to be, I think it's 32. 32. Yeah, 2, 4, 8, 16, 32. Yeah, okay. So we get 32, and now we subtract 4 from both sides and multiply by 32, and we'll get c is equal to 32. So there is our constant is determined by our initial condition, and now we get our final solution. So therefore, y of x is equal to x squared plus 32 divided by x to the 5th. There we go. All right, perfect. So there is our solution, and let's go ahead and head over to Geogebra and see how well Geogebra handles a first order linear differential equation. So we'll do a Geogebra demo right here. Okay, so here we are in Geogebra. Now, let's see. So what was our differential equation? So in order to describe our differential equation, I guess we need to solve it for y prime, because whenever we say solve ODE, it wants to know, y prime is equal to this, function, which they're writing it as f prime of xy. But so it always has to be y prime is equal to this formula of x and y. So I guess let's start with the field equation. So maybe I'll just write it down quickly here. Recall that our equation was like y prime plus, 5 divided by x times y is equal to 7x squared. Okay, I don't know what will happen when I don't know. Maybe that's the solution. I don't know. No. Anyway. So that's the idea. And if we solve that for y prime, then we'll get the following. So let's type slope field, and solving for y prime, we get 7x minus 5 divided by x times y. There it is. That's our slope field right there. Okay, very interesting slope field. Something interesting is going on there. Maybe we'll zoom in a little bit to see. It almost looks like some kind of parabola here or something. But a lot of different slopes right in this area here. Okay, so let's go ahead and try to solve this ODE and see what we get. So solve ODE, 7x minus 5 divided by x times y. Aha. Oh, okay, so it gave us x to the 7 divided by x to the 5th. which actually is just x squared. So that would be the solution when C is equal to 0, or when the initial condition, well, I don't know what initial condition that would be for x equals 2. I guess I zoomed in a little too much. We can zoom out. Still, yeah, it's hard to see. Yeah, so x2, and then it's the initial condition we want is like 5, right? So we actually want to go through this point right here, but we're not going through that point. So let's go ahead and let's play this. Let's see what happens here. Aha, okay, so there we're sort of seeing the picture. And I guess we're mostly interested in this right-hand side because the initial condition is when x is positive, but there is this other piece of the solution over here as well on the negative side. Oh, okay, great. Oh, very nice. Okay, so let's stop that. And let's go ahead and ask for the solution that's going through that point. So 7x minus 5 divided by x times y. And then the point we want to go through is 2, 5. And that, yeah, that's our solution right there. That's exactly what we had. You know, we simplified it a little bit, but that is exactly our solution. Very nice. And you can see, if I scroll down a bit, you see that going through the point, actually, so so I have to kind of zoom in a little bit more. What it's indicating there with that dot is actually the minimum value of the function, which is not quite at 2. It's a little bit less than 2. But if you zoom in enough, then you can see that indeed that function is going directly through this. Maybe turn off the slope field, but it's going directly through that point 2, 5. Yeah. Very interesting. Yeah, so you see how much this function is changing slope in this sort of region, kind of in the region of that parabola y equals x squared. A very interesting solution. Okay, so let's head back to the notes now. Okay, we're back. So let's move on to our next example. So example number 2. So we need to put this again into that standard form. And remember, the standard form is y prime plus p of x times y is equal to q of x. So that is the standard form. So in order to do that, we'll need to divide by x. So we're dividing by x so that x cubed becomes x squared. And then I guess I want this y term to be on the left-hand side of the equation. So I'm going to subtract that over. And just to make it clear, I do want a plus there. So I'm going to say plus negative 2 over x times y. Oops. And therefore, let's just write down our formulas here. P of x is equal to negative 2 over x, and q of x is equal to x squared cosine x. Okay. So notice that this question doesn't have an initial condition, so we're just going to be finding the general solution and then we'll be done. All right, so what's the first step that we do when solving a first order linear equation? The first thing we do is we compute this integrating factor. It's the exponential of the integral of p of x dx. So this is going to be the exponential of the integral of negative 2 over x dx. So that's why it was important to have a plus there. because that negative has to be part of this, this row calculation. And let's see, what do we get? So exponential of, so this will be -2 times the logarithm of the absolute value of x. Okay. And I'm going to just take, so I know there's like a -2 here, but let me just take the 2 part, I'll leave the negative sign there. I'll take the 2 and put it up here. And then this will allow us to make the following observation. So we're squaring the absolute value. And I guess let's just make a note here that the absolute value of x squared, this is just equal to x squared. And you can try like a few different values of x to convince yourself that that's the case. But the absolute value is either going to be x or minus x. And x squared is x squared, and minus x squared, the whole thing squared, is going to be, that will also be, because you'll square the -1, so we'll end up getting -1 squared, which is 1. So we'll just get 1 times x squared. So that's why we get that. Okay. So with that observation, let's go ahead and write this as the negative log of x squared. And now actually, in order to cancel this exponential and this logarithm, I'm going to move this up here as well. So I'm going to be doing x squared to the power -1. So x squared, so it's like x squared to the power -1, right? And what do you do when you raise one power to another power? You multiply the powers together. So this will become x to the -2. And now we can cancel exponential and the log, and we will get that the integrating factor is equal to x to the -2. And let's put a box around that. So there's our integrating factor. Okay, and I'm just going to add a page to my notebook. I'll be right back. Okay, I'm back. Yeah, I always want to pause the screen when I add a page because I had a problem with that one time, and I'm paranoid now. Okay, so there's our integrating factor rho. Now we're going to multiply this equation right here. We'll multiply this by that integrating factor, which is x to the -2. Okay, so let me just grab this because I'm afraid I'm going to forget exactly what it is. So I'll grab that, put it down here. So there's our equation. And now let's multiply both sides by x to the -2. And now I don't need that plus anymore. I'll just replace it with the minus like that. Okay, distribute. Let's see. So this will be x to the -2 and then divided by x. So that'll end up becoming x to the -3. So I'll get -2 x to the -3 times y. And then over here, the x to the -2 and the x squared cancel. So I will get cos x. Okay, perfect. And now we do the thing we normally do when solving linear, first order linear differential equations. We make the observation that if I take the derivative of this function, I get this function right here. And that is true. So the derivative of this would become -2 times x and then subtract 1 from the exponent. So I end up getting -2 times x to the -3. So there we have our product rule. So we can go ahead and write this down as the derivative of x squared times y. Oops. Derivative of x to the -2 times y. And what happened to my cos x? Okay, he's been restored. Perfect. Okay, so that is equal to cosine x. And now we integrate both sides. Plus a constant. Integral of cosine is sine x. And if I take the derivative of sine, I do get cosine x. So that is the correct antiderivative, plus c. And then I'm going to divide both sides by x to the -2, which is equivalent to multiplying by x squared. So I will get x squared times sine x plus c. And that's our final solution. All right, very nice. Well, let's go ahead and head over to Geogebra and see what this thing looks like and see if Geogebra can solve this differential equation. So I'll be right back. Okay, we're back. So we're solving this differential equation in Geogebra. And let's see, I'm gonna take that standard form and then write it, put everything to the right-hand side. So it's gonna be y prime is equal to, that'll be 2 divided by x times y plus x squared times the cosine of x. And I think that should do it. Yep, there it is. Okay, so there's our slope field. And we don't have an initial condition, so we're not going to worry about any particular initial condition, but it'll be interesting to see how the solution animates. So let's solve this ODE. 2 divided by x times y plus x squared times cosine of x, cosine of x. Oops, solve ODE. Solve ODE. Yeah, perfect. Okay, give it some time. And it was able to solve it. Does that kind of match our solution? Let's see. Yeah, that's when c is equal to 1. We get that solution there. Okay, let's animate it and see what this function looks like. Might have to zoom out a bit to really get a nice picture. Oh, okay. Oh, wow. Okay. I see. Yeah, let's zoom out a bit. I think there's definitely some interesting stuff happening at a bigger scale. And you look at that slope field, those, you know, the slope field lines are basically vertical, right? And you see, whoa, okay, I see what's going on. Yeah, so this thing is oscillating, you know, up and down because of the sine of x, but then as you move away from 0, that x squared gets really large. And so that's why the magnitude of this sine x goes crazy. Okay, very interesting. Okay, so Geogebra was able to solve this equation as well. So Geogebra is doing a pretty good job for us so far. So it looks like Geogebra can handle linear first order equations pretty well, So do experiment with it yourself and see if Geogebra does a good job for you on these types of equations. All right, so we're back, and so that was excellent. So let's now move on. So one last thing to look at today are this really nice application of first order linear differential equations, which are these mixture problems. So we'll see that we can actually analyze how the concentration of some kind of a solute in a mixture. So for example, like salt water. So we have water and there's a certain amount of salt that's dissolved in the water. And we can measure how much salt is in that water using a concentration measurement. So for example, grams per liter as a way to measure how much salt is in the water. So we have some, salt water coming in here with a certain concentration, which is given by this concentration in. And the rate at which this mixture is flowing in is given to us by R in, which is the rate of the mixture flowing into the tank. And what is the units for that? So that would be like volume per time. So for example, liters per minute. And we'll also have, we'll need to know, in order to fully understand what's going on in this tank, we'll need to know what the initial volume of the mixture in the tank is. So how much stuff is in here initially, and that will be given to us in liters or some unit measuring volume. And then we'll also need to know how much salt is in here initially, and that will be given to us using some sort of measurement for mass. So for example, grams. Okay, so V naught will be our initial volume, and X naught is our initial amount of solute in the tank. So solute is going to be our like the salt, for example, mixed in with the water. And the other things that we'll need to know are what is the rate of flow coming out of here? So we need to know the rate coming in, and we need to know the rate coming out. So the rate out is going to be R out, and that will be, again, in the same units as R in. It'll be like volume per time. So that will be like liters per minute. And then we'll also need to determine what is the concentration coming out. And in the example, we'll do this concentration coming in. This will just be like some constant. So we have some source of mixture and it has a constant concentration and it's flowing into this tank. But as time goes on, the concentration coming out, it depends, right? Because the amount of concentration of the solute inside the tank is changing. For example, we could start out with like pure water, right? So there's no salt in here at all. And then we start pumping in salt water. So initially what's coming out of here is just pure water. But as soon as we start pumping in some salt water and we're like mixing this stuff up like all the time. So as soon as we get some salt water coming in here and it gets thoroughly mixed, and then we start getting salt water coming out of here. And so we see that initially C out is 0, but then as time goes on, the C out will be increasing. So that's why we'll have to pay attention to that. So the C out will be actually a function of time. It's going to change, but everything else we can think of as being just fixed values. And what we're interested in knowing are a couple things. We want to know how the volume of the mixture is changing over time. So V of t will be the volume of the mixture at time t, measured in some units like liter. And X of t will measure the amount of the solute at time t inside the tank. And that will be given by, for example, grams as our unit. So I want to go over like how we can formulate this differential equation using a technique that's actually very, very useful in a variety of different situations. So whenever you're faced with some kind of problem like this where things are changing over time, a good way to figure out what is the differential equation that models this thing that I want to measure. So a very good way to think of this is to just, instead of thinking about like instantaneous rate of change, instead let's think about the change that's occurring, you know, when we have a very small change in time. So we'll say the delta t is like some very small change in time. So we're thinking about going from some time t to a time t plus delta t, right? So a very small change in time. You know, if we're measuring in minutes, then maybe this delta t is like just like a second or a fraction of a second or something like this. And then we want to, well, we're interested in two quantities, right? We're interested in v and x. And we want to write down some equations which tell us, like, you know, after this amount of time here, what is the, how much has v changed, right? So what's the change in the volume after these small amount of time delta t? And also, what is the change in the amount of the solute after a small amount of time? Okay, very useful technique, and you can make a lot of, you can get a lot of mileage from this technique. So let's have a look at how we can use it here. So we're thinking about, first of all, V. Let's think about the volume. After delta t minutes, how much additional liquid is being added to the tank, and how much liquid is being removed from the tank? Well, we know that the rate coming in is Rn, and that's measured in liters per, this was liters per minute, right? So liters per minute was the rate there. So in order to get the amount, we would multiply the liters per minute by some amount of time measured in minutes, and that will give us liters. So we'll do Rn times delta t, and that will give us the amount of liters that are added to the tank after a small amount of time. And by the same reasoning, the amount of liquid that is streaming out of the tank is going to be this rate R out, which is also liters per minute. And when we multiply that by minutes, some amount of minutes, that will give us the amount of liquid in liters that is removed from this tank. And now we basically have exactly what we want. So how much is the volume changing in this small amount of time? So the amount of change in V will be just the amount that we've added, and then subtracting the amount that was removed. And there it is. That's basically the formula that we wanted right here. So there's our formula. And what do we do with that? Well, notice that if we divide both sides by delta t, then we get this formula here. And that looks, this thing here looks a lot like a derivative. In fact, you can argue that if you let the delta t now go to 0, then this delta t over delta v over delta t is actually the instantaneous rate of change of the volume with respect to time. And that is equal to R in minus R out. So there is our differential equation for the volume. And we have also an initial condition. So V of 0 is V naught. And what's nice about this differential equation is that it is separable. So this is a separable differential equation. We can separate the variables by taking this dt and multiplying it up here. And on the left, we'll just get dv. So we'll integrate dv, and we will integrate the right-hand side, which is Rn minus R out times dt. Integrating the left-hand side, we get v. Okay, so that's easy. And then integrating the right-hand side, this is just a constant, right? So it'll be that constant times t plus our constant of integration, which is c. Oh, I made a mistake here. 1 second, I need to fix this. This should be v naught. Yeah, so if you now use the initial condition, then we see that when we plug in 0 for the t, then this will be equal to c. So the v of 0 is c, and so v of 0 is v naught, so that must mean that c is v naught. And I do have this equation here is correct, so that is perfect. So there's our formula for the volume of how the volume of the liquid is changing in the tank over time. All right, now let's go through the same type of argument for x of t. So for x of t, we're going to need to determine how much of the solute is added to the tank after a small amount of time, and how much of the solute is removed from the tank after a small amount of time. So just kind of looking at the units here, maybe I'll just quickly write this in below. So this will be the rate coming in, liters per minute. And then we have, so liters per minute. The concentration was grams per liter, and the time is in minutes. Right, so if you just kind of quickly check our units, then we're going to see that we have L divided by L, so those cancel, and the minutes divided by minutes, those cancel, and so the unit here is going to be grams. So that's kind of why we can argue that this is the formula. But it makes sense, right? If we want to measure the amount of solute that is added, you look at the amount of liquid coming in per unit time, you multiply that by the concentration, and that will give you the amount of solute per unit of time that is coming in, and then you just multiply that by delta t, which is the amount of time, and that will give us the amount of solute that is added over that small amount of time. And the same argument for the amount coming out, except we do have to remember that the C out is a function of time, and so we'll have to figure that out below. But for now, let's just leave it as C out. And because the C out is a function of time, I can't really say that the change is exactly equal to this. So I just know that it's approximately equal to this amount, because this is not just like a constant thing anymore. This is also changing over time. But this is a fairly good approximation here, just taking this, this function, multiplying by this, small amount of time. So when we divide both sides by delta t, then we're going to get that this delta x over delta t is approximately equal to this. But remember that C out depends on time. So actually C out is a function of time. And if you just figure out what it should be, it's obviously the concentration of the liquid coming out. It's the amount of solute in the tank divided by the volume of the tank at time t. And so that gives us this formula here for C out. So let's plug that in here, and we get x of t over v of t. So this is kind of like measuring the concentration at the beginning of our small interval of time. And obviously that's changing, during the interval. No, that's why we have to put an approximation here. It won't be exactly equal to this, but it's a good approximation. And as delta t goes to 0, this approximation will actually become an equality, and this delta x over delta t will become the instantaneous rate of change, dx dt. And let's see, so what do we have here? So I just when I did this, I also just moved this over here underneath the R out because I wanted to get the X on its own. So that way we can see that this is a differential equation where we're trying to solve for the function X of t. Here's the derivative of X, and it depends not only on time, but it also depends on X itself. All right, and our initial condition is X of 0 equals X naught. Now, before with volume, it was a separable differential equation, but in this case, this is a linear differential equation for X. And we just learned how to solve linear differential equations, so let's go ahead and do an example where we write out this differential equation, and we will see that it's linear, and then we'll solve it using our integrating factor technique that we just learned. So here's the example, exercise number 36 from the textbook. So it says that a tank initially contains 60 gallons of pure water. So what does that mean? So initially, so that means we're going to have, so V naught will be 60. We'll write this down below, but just sort of mentally keeping track of what this means. Pure water, that means that the initial concentration in the tank will be 0, right? There's no salt in the tank. Yeah, and we are talking about salt here, by the way. Salt and water. So what is coming into the tank? So we have some brine containing 1 pound of salt per gallon. So we have a pound of salt per gallon entering the tank. So that means the concentration in is 1 pound per gallon. And it's entering the tank at 2 gallons per minute. So that is the rate coming in. So R in is 2 gallons per minute. And so obviously if we just kind of multiplied those together, 1 pound per gallon and 2 gallons per minute, that means that we're getting 2 pounds of salt coming into the tank per minute. And then the perfectly mixed solution leaves the tank at 3 gallons per minute. So that is our R out. R out is 3 gallons per minute. And what do we want to find out? We want to find out exactly what the amount of salt in the tank is after t minutes. So we want a formula for this amount of salt in the tank, X of t. So we need to solve for X of t. And after we have X of t, we can determine what is the maximum amount of salt ever in the tank. So we'll be able to maximize this function and figure out what is the maximum amount of salt ever in the tank. And that might be interesting because there might be some regulation that says that we can never exceed a certain amount of salt in the tank. And we need to be able to figure out what that maximum is because we may have to adjust some of these factors in order to make sure that maximum is below a certain threshold. Okay, so let's go ahead and solve this differential equation, or solve this problem using differential equations. So let me try to summarize what I think we had from above. So we had V naught was 60 gallons. X naught was 0 pounds, right? Because we're measuring it, the salt in pounds. The concentration in was 1 pound per gallon. And the rate coming in was 2 gallons per minute. Yeah, just making sure I got, yeah, per minute, 2 gallons per minute. And finally, the rate coming out was 3 gallons per minute. Okay, so let's see. Yeah, okay, great. So what was our formula for V of t? So V of t was R in minus R out times t plus V naught. So V of t is going to be 3, oh wait, it's not 3. So 2 coming in, 3 going out, and that is 60. So if we simplify that, we will get 60 minus t. And what this tells us is that the tank will be empty after 60 minutes. Okay, so the tank will be empty after 60 minutes. So after 1 hour, the tank will be completely empty. Okay. Now, we need to set up our differential equation for x. And the differential equation was that we have the, it was the rate coming in times the concentration coming in. And then we're going to subtract the rate coming out times the concentration, let me put a dot here, times the concentration coming out. Yes, that was it. Okay, but we know that the concentration coming out, this is a function of t. And what was the concentration coming out at time t? This is the amount of solute in the tank at time t divided by the volume, right? That's how you measure concentration. Okay, so what is our differential equation then? R in was 2 and C in was 1 pound per gallon. And then R out was 3 gallons per minute. And then we have this x of t over v of t. So I will put that, yeah, let me just put that x of t divided by v of t. So 2 minus 3, v of t was 60 minus t, 60 minus t, and then times x. So it's x of t, but I'll just call it x. So here's our initial condition, and also we know that x of 0 is 0, right? Because the tank initially contains pure water. So there's our differential equation, and it is linear, so let's put it in the standard form. So we have the derivative plus 3 over 60 minus t times x is equal to 2. So this is linear, and our p, so it's not p of x this time, it's p of t, because t is the independent variable. So p of t is 3 over 60 minus t, and q of t is 2. So let's compute our integrating factor. This is the exponential of the integral of p of t dt. So exponential of 3 over 60 minus t dt. All right, let's see. So this is going to be like 3 times, it'll be some kind of logarithm of the absolute value of 60 minus t, But if I take the derivative of that, because of the chain rule, I would have to multiply it by -1. So in order to fix that, I'm going to put a minus sign right here. And if I check, if I take the derivative of that, I do get the correct thing right here. Now, if you want to go through this maybe in more steps, you might want to do u sub, right? So you could, if you want to do u sub, you could say u is equal to 60 minus t, and then just go through the u sub. And that's a way to do it sort of carefully step by step. But if you already kind of know the form of what the answer should be, it's just a matter of writing down that logarithm and then just carefully making sure that everything has the right, that this coefficient out front is correct. Okay, so let's continue. Now, since t is going to be between 0 and 60, right? We're going to stop at 60 because that's when the tank is empty. So t is between 0 and 60. I guess we're kind of thinking about, yeah, because I don't want to put log of 0 in there. So maybe we'll say t is between, starts at 0 and then, approaches 60. Yeah, that's good. So in this region, we're going to have that this absolute value of 60 minus t is equal to 60 minus t, because that 60 minus t will be always positive. So we can drop that absolute value and we'll get the exponential of -3 log 60 minus t. So again, logarithm means that I can move that up here. So I will do that. And then I will also, after I do that, I can just cancel this exponential and this log. So I'm going to do both at the same time, and that will give me 60 minus t to the -3. Okay, perfect. So what do we do with this? So we're going to take this integrating factor and we're going to multiply both sides of our differential equation, this guy right here. So I'll grab this and head down here. So let's multiply both sides by this 60 minus t to the -3. So that'll be times dx dt plus 3 over 60 minus t times x is equal to 60 minus t to the -3 times 2. So 60 minus t to the -3 dx dt plus, this will be 3, yeah, I'm just making sure, yeah, 3, and then divided by, this will be 60, well, maybe I'll write it this way, so it'll be easier to see. So it'll be 3 times 60 minus t to the -4 times x. And that's 2 times, let's write this as 2 over 60 minus t cubed. Okay, and again, now we can see that if I take the derivative of this, I do get exactly this thing right here. And that means that we do have a product rule, so we can write this as dx dt this time, right? This is dx dt. Dx dt of 60 minus t to the -3 times x is equal to 2 over 60 minus t cubed. So now we integrate both sides. Integrate. Okay, and we will have a plus c here as well after we integrate. Let's see. Okay, so we want to integrate this. Let's see. Why don't we go ahead and do the u sub carefully? So let's just u sub this carefully, just so we don't make any mistakes. So I'm going to let u be that, and that means that du is equal to negative dt. Okay. And let's see, so the integral will be negative, so dt is negative du, so I'll get negative 2 over u cubed. Let's write that as negative 2 u to the negative 3 du. Okay, that's good. All right, what's the antiderivative of that? So that'll be like u, we need to add 1, so it'll be negative 2. And then what do we need to multiply by? Let's see. Oh, if I take the derivative of that right now, I do get exactly negative 2 u to the negative 3. So that is actually what we want right there. So that's it. So now we get 60 minus t to the negative 3 times x is equal to, and then plug that u sub thing back in. So that's 60 minus t to the negative 2 plus c. And now we're almost done. We almost have our x of t. We just multiply both sides by 60 minus t to the power 3. And that will give us x is equal to 60 minus t to the 3 times the 60 minus t to the negative 2 plus c. And x will then be, let's see, so 3 minus 2 is going to be 1. So we'll get 60 minus t. And then we'll also have plus c times 60 minus t cubed. All right, that is our general solution right there. So that's our general solution, but in order to figure out what the c is, we have to plug in, we have to use our initial condition. So x of 0, so initially it was pure water in the tank. So we'll get 60 minus 0 plus c times 60 minus 0 cubed is equal to 0. And let's see. So that will be c is equal to negative 60 divided by 60 cubed. Let's see, 60 cubed, right? But that's then just negative 1 over 60 squared. 60 squared will be 3,600. Okay, so therefore x of t, yeah, let me just put it on the next page. So x of t is equal to 60 minus t, and then minus 1 over 3,600 times 60 minus t cubed. Yeah, that's it. That is our final solution. So that's the answer to part A. So let's go ahead and check this in Geogebra and see what we get. Okay, so here we are in Geogebra, and our slope field for this differential equation will be given by, I'm going to change the t to an x and the x to a y. I don't think it's absolutely necessary, but just in case. Well, I guess I could try doing the 60 minus t, see what happens. But if it's not good, then we'll, guess it's okay. Is it? Everything looks like the same slope. Maybe that's fine. I zoom out. Oh no, yeah, okay, that's fine. Yeah, you see the slope field changing. Okay, so that's fine. So we can use t and x. Perfect. Okay, so let's solve our ODE. So solve our ODE. It's 2 minus 3 divided by 60 minus t, and then times x. So let's see if it can give us a general solution. Doesn't look right. let's change this. So maybe now we actually have to change it, x and y. Okay, no, that's matching the slope field. So I think we're probably okay. I don't know if much is going to change by changing the c value here. Just let that play. What we're interested in is the solution of this differential equation. Oh yeah, okay. So that's doing something. So we want the solution of this differential equation when, so let's enter the differential equation in again. Looks like it always has to be x and y for this. Yeah. And then we want the solution that goes through 0, 0. Oh, okay, great. Right, so let's just move this over here. Well, actually, I guess the part that we're interested in is this part right here. Yeah, there's we're just interested in, starting at 0. Let me get rid of this. I'll put the slope field on though, that's kind of cool. So we're starting at 0, and then the concentration of the salt is increasing until it reaches a maximum, and that's the question we want to answer for part B. And then it will decrease down to 0 again. And actually that makes sense that we get 0 solute because we know the volume is also going to 0 at that time. So that's essentially the curve that we're interested in, starting from 0 and then going until 60. And then what is this maximum? So let's see if I click on it. Actually, Geogebra knows that the extremum is going to occur at the time of 25.35898 something minutes. So that's the time. So about 25 and just trying to think how many seconds that would be. Anyway, so less than 25.5 minutes, we will achieve a maximum of about 23 pounds of salt. And that will be the maximum amount of salt that will occur at about, shortly after 25 minutes. Okay, so that's good. So of course we could do this by hand. We would use calculus to take the derivative of this function and set it to 0, and then we could solve for this exactly. So why don't we try that and see what we get. Okay, so that was part A. I guess I could put like an A here. I mean, the A started above, but so let's do part B. So part B says, what is the maximum amount of salt in the tank? So to do that, we would need to find the derivative of this function. And so let's go ahead and take the derivative. So we'll get -1 and then minus 1 over 3,600 times 3. So we're doing a power rule and then the chain rule here times -1. Okay, so there's the derivative. And we're going to set that equal to 0 and solve for t. Okay, so let's see. Oh, okay, so this negative will cancel this negative, so I'll be a positive, and I'll just move this guy over to the right-hand side. So that will give us 1 over 3,600. I guess it's 3 over 3,600. Oh, that'll simplify too. Let's do that. So that'll be 1 over 1,200 times 60 minus t squared. And that will be equal to 1. Multiply both sides by 1,200. And let's see. I guess we'll take the square root. I guess we'll have to figure out if it's the positive or negative one. So let's just take the square root and then think about this a little bit. Let's see. So it'll either be positive or negative square root of 1,200. And then that means that the t will be equal to 60. And if I move that over, it'll be minus positive. I guess I'll write it that way. So the sign will flip, whatever one we chose up there. Minus plus, let's see, square root of 1,200. So what is the square root of 1,200? It's going to be smaller than 60, I think. Yeah, 34. It's about 34. So it'll be smaller. So I guess either way we choose it, it's going to be a positive time. So that's not a problem there in terms of getting a negative time. But we do know that the tank is going to be empty after 60 minutes. So this time that we're looking at, it's definitely not larger than 60. It's actually the one that is smaller than 60. So that would be, so note t, well, we know it's going to be strictly between, 0 and 60. So that means that the t we're interested in is going to be the one that we're subtracting this square root of 1,200. Okay, so then t, if we could simplify that a bit. I guess it doesn't, do we need to do that? Because I could factor out like 400 from that square root, which is 20 squared. So I guess I could get minus like 20 times. And if I factor out 400, that will leave me with 3. So that should be it right there. And what is that? What is that time? 60 minus 20 times the square root of 3. Yep, that's exactly what Geogebra said. So this is actually equal to 25.35898, and it goes on from there. So but it's exactly the digits that we got from Geogebra. All right, then to figure out what the maximum salt is, we have to plug that back into our formula for x of t. Let's see. So that would be this guy here. So So just to recall, that's that guy. And this is kind of, well, I'm not sure if I really want to do this all by hand. I mean, I could just do this on the computer. I don't know if I want to do this exactly, but let's try. Hopefully this doesn't get too annoying. Let's see. So 60 minus 20 root 3, and then minus 1 over 3600 times 60 minus the 60 minus 20 root 3 cubed. So that means this x of this time where the salt is maximized, it's going to be, let's see, so this 60 cancels that, and we'll get plus 20 root 3. So I get 20 root 3, and then minus 1 over 3600. And let's see, so again, the 60 will cancel that one, and I'll get 20 root 3 cubed. So that'll be 20 root 3 cubed. And is there anything I can do to really simplify that? Let's see. 20 cubed. That's like 8,000. And then I can multiply that by, I can square 2 of those root 3s, and then I'll get 3 root 3. Okay, well, 8,000 divided by 3,600, that's 20 over 9. Okay, so I get 20 root 3 minus 20 over 9. Oh, times 3. I forgot to multiply by 3. Times 3, that's 20 over 3. Okay, so 20 over 3 root 3. So we could factor out the 20. We get root 3 minus root 3 over 3. And yeah, I don't know. I guess that's probably as good as it gets. Let's type that in and see what we get in the computer. So square root of 3 minus square root of 3. I guess I could factor out let me factor out that root 3. Yeah, I'll factor out the 20 root 3. Yeah, that's better. What was I thinking? So it's 20 root 3, and then that'll be 1 minus a third, which is 2/3. So that'll be 40 root 3 divided by 2. Okay, that's actually a lot cleaner than I thought it would be. So let's type that in. 40 times square root of 3 divided by 2. Oh, divided by 2. So it's just 20 root 3. Yeah, 20 times square root of 3. Okay, so it is a nice clean answer. Oh yeah, so and this 20 square root of 3, that in fact is like 34.641, and then it just goes on from there. And wait a minute, we wanted, the extremum was supposed to be 23. I may have made a mistake. Let me just pause and see if I can spot my mistake here quickly. Okay, yeah, I found the mistake. So the problem was here. So I was supposed to multiply by 2/3, and I did not. I just like removed this big mistake. So this is going to be 40 over 3. Yeah, so this should be 40 root 3 over 3. So let's fix that. So 40 root 3 over 3. And that is our final answer right there. And that is going to be equal to, big drum roll here, 40 times square root of 3 divided by 3. Yeah, there it is. Okay, now that matches GeoGebra. Great. So 23.09 and so on. So that is our final answer. Okay, so therefore the maximum salt ever in the tank is about 23.09 pounds, and happens after about 25.36 minutes. So there we go. 23.09 pounds and happens after about 25.36 minutes. So imagine if maybe there's a regulation that says you can only have a maximum of 20 pounds of salt in that tank due to safety regulations, then we have to do something, right? We have to change something now that we know that it's actually going to go up to like 23 pounds of salt. Okay, so that's a good place to stop. And thank you for watching this lecture. And I will see you in the next one. Make sure if you have any questions to email me, contact me, or come to my office hours, make an appointment, and I'll be happy to answer any and all of your questions. Okay, take care.